Okay, let's take a look at number 3. Number 3 is talking about adjusting admission prices to an event, right? And then the fact that if you raise the price, you're likely to lose some people, right? So if you've actually had somebody, you've done the analysis and you figured out that it behaves this way, and of course this is simplistic, but it still actually applies to a lot of situations in reality. A lot of us started by just setting up a table based on what was directly given, right? If you raise the price, then you lower the people by 100. And then for each of these price raises of $5, you drop the number of people by 100 people each time, right? And then you continue calculating the total money you make. The only thing is, you could keep going with this for quite a while and make a very large table if we keep going up by 5s. And you're going to find that this price keeps increasing, increasing, increasing. So it might seem at first like, this doesn't really seem to be working, but you can think, what are some other tools in our tool belt that we could start using to do this? One thing you could do is you could start jumping by more than just 5 in the price and then kind of make that continually jumping by that amount, and then your table won't have to get so big so quick, possibly. So for example, if I jumped up by 20, that's 4 increases of $5, so I would need to drop by 400 people, and then that would give me this income. But again, if you kept going, you'd probably see that it's still increasing. It hasn't decreased yet at all. So you could certainly do that. You could even start going by even like 50s or whatever. But if you start jumping by larger increments, then you'd probably get somewhere where eventually you'd see this go down again. Remember, quadratic. And then maybe you could hone in and try to get more precise about the price after that point. So that's a great way to go about this and solve it. There are more methodic and less cumbersome ways, I guess I would say, that we could do this that I'd like to talk about. One of them actually was brought up it's brought up by students. Usually someone brings this up every year. Someone suggests, what if I use a difference table? Let's actually take a look at that and see if that could help me out here. So, if we were to use a difference table, I love the suggestion again that some of you guys made to use that. You'd actually see that it turns out the second differences are constant, so it does fit a quadratic. The only thing here is, it's a little bit weird for this one because this one has like 2 inputs. We can almost think of this as like input 1 and this is input 2. Because in order to get my output for the money I make, we had to multiply these 2. So setting this up would be weird because you'd have to be like, wait, what's my input? What's my x? I can't have 2 separate ones. It turns out actually the way to think about an input here is not either of these. These 2 essentially helped me calculate the output, but the actual input would be the number of price increases. So right now at 50, we haven't increased the price at all, right? But remember, every $5 increment increase represents a 100-person drop. So here's one price change, right, of $5. If I change twice, that just means I've increased the price twice. And remember, each one is an increment of $5. And then 3 times, 4 times, etc., etc. Now, actually, this is what our input is, and these are what our outputs are. And we can go ahead and apply what we learned before in order to figure out a quadratic function for this. The quadratic function that matches this, if you remember, if you take half of the second difference, right, the constant difference, that's always going to get our a value. And remember, this method goes with normal form, so ax squared plus bx plus c. The next one that's easy to find from the table would be when the input is 0, that output is always our c value, right? Because you can see when we make x 0, that's all gone and that's what's left. So 500,000 is when x equals 0. And then remember how we had to play with it? Like we had to plug some values in for x and y to figure out the b value. And I did that work ahead of time and I got 45,000. Now the great thing of this is, remember, we know this is quadratic. We talked about how this is increasing and then decreasing again. It's going up and coming down. So we have an upside down parabola. Well, if we want the highest possible revenue, and this quadratic represents revenue, that means the vertex, right? What's the vertex of normal form? Well, we know that it's x value is negative b over 2a. Negative b over 2a. So that's negative 45,000 over 2 times negative 500. And if you simplify that, it just becomes 45, because this becomes negative 1,000. When you divide that, 45. So what this tells me is, be careful, we're not done yet. That doesn't mean $45 is the price, because remember the question asked, at what price should we charge to maximize our revenue or our money? Or to get the largest income, it says, but that's what we mean. Okay? Remember that our X represents the number of price increases. And so there's one last thing that has to be done. I figured out that 45 price increases is what's going to give me the most money. So since the question asked at what price, I have to start with my $50 and increase 45 times by $5. That's all. So my final answer, 50 plus 45 times 5. And if you do that, you get $275, which is just what we got. If you had done the table method, you would have kind of got it down to 275 if you were really precise with that. Now here's the interesting thing. This is super awesome way to do this because it applies what we've learned in the past and all these things, but something we've learned in the recent past can be used for this. And if you're a little bit creative with this, I've seen groups that came up with this when we were working on this with you guys. Let's look at one more method that's actually even less work than this, I think, to figure this out. So this is my personal method of choice for solving this one because I just think it's way more beautiful and kind of seamless, but either way, if we just generalize this and we say the number of price increases is X, you'll notice that to get here, first of all, actually, I want to mention something here. Notice that each of these is linear. So essentially what we're saying is we have a linear thing, right? Because this is 50 plus, a certain number of x's, right? And you probably realize that this has 50 plus 5x if we let x represent the number of price increases, right? And the people start at 10,000, but they decrease by 100 each time. So you can probably realize that this is 10,000 minus 100 x. And again, that x is dependent upon how many times you've increased the price, right? So you have a linear times a linear, and we've learned that a linear times a linear is always equal to a quadratic, right? So if this is an expression representing my price increases, and this is an expression representing the people and how they decrease every time we do that, then how do I calculate my revenue? If I were to actually make this r of x into an actual function, what did I do with this and this? I multiplied them, right? So if my price increases were x, then my revenue is 50 plus 5x times 10,000 minus 100x. And this actually is in 2-point form. Watch what we can do here. We can factor a 5 out of this, and we can get 5 times 10 plus x. And we can factor 100 out of that guy, and that'll leave me with 100 minus x. And then I'll just put this 105 together, so I get 500 times 10 plus x times 100 minus x. And this is my revenue function rewritten in a simpler way, basically. And if you notice, technically this is 500 times that and plus 0. This should look like 2-point form. So an output of 0 would happen for 2 different values. So watch this. If I have my 2 points, negative 10 makes it become 0. Negative 10 gives me 0. And then positive 100 for this x, right, will give me 0. Well, we already know the vertex is always halfway in between the 2 points. So what's halfway in between negative 10 and 100? If you play with that, you're going to see that 45 is halfway between. And guess what? That's what we already came up with using the other way. And 50 plus 45 times 5, exactly the same that we calculated before, is $275. So there's the thorough thinking process for tackling that problem.